this video, we are going to discuss the solution for replace with sum of larger. In this question, we need to replace a node's value with sum of all nodes that are greater than it. Okay, so for getting to this solution for this question, we need to know a special property of binary search tree, which is that the in-order traversal of a binary search tree will give us sorted order. Okay, now first of all, let's see if it is true or not. All right, so let's see in order traversal for this tree. So we will visit 10, then 20, now 30, then 40, then 50, then 60, then 70, then go back. All right, we have got a sorted order. Now you must be wondering why we got a sorted order. If you remember what a binary search tree is, you will remember that the left value is smaller than the parent's value and right value is greater than the parent's value. So a parent is our node and left child and right child are, this is smaller value and this is larger value. So it looks like this. Our left value smaller than our node and our right value is greater than our node. Now if we write in order, what we do is we call left first, then we go do some work for node, then we call our right child. So because of this, we got a sorted order. Now if we will write reverse in order for any tree, what we will get is larger value first, then smaller value, okay, larger right value, then smaller node value, then smaller left child's value. All right, if you do reverse in order, okay, let's write our tree again. 40, 20, 60, 10, and 30, and it was 50, 70. So if we will do the reverse in order for this, we will get 70 first, then 60, then 50, then 40, then 30, then 20, and then 10. So we need to replace it with sum of larger. So we are going to use a static integer known as sum, and we are going to add our larger value each time we visit it. Okay, now we are going for in order. So we reach 70 first. Now we are going to replace 70 with a value which is kept in sum. So it will become 0. Now we are going to add 70 to our sum. Now why I have written 0 for the 70 here? Because there are no elements which are greater than 70 in this tree. Alright, now we move on to 60. So there is only one value which is 70 greater than 60. So we are going to replace 60 with 70, and we replaced it. Now we are going to add 60 to our sum. Now we are going to replace 50 with sum of 60 and 70, which is 130 now. 130. 50 is replaced by 130. And now we are going to add 50 to our sum. Now we reached 40. Now we are going to replace this with 180. 180. And now we are going to add 40 here. So now we have sum's value as 220. Now reverse in order, so we will reach 30. So 30 is going to be replaced by 220. Okay, now we are going to add 3 to it. So now it becomes 250. 20 is going to be replaced by 250 and we are going to add 20 to our sum. Now we have 270. Now 10 is going to be replaced by 270. Now there is no need to add 10 to it because we have 10 will be the last element that we are going to visit in the reversing order. Okay, so let's write the code for this and see if it works. So first of all, let's see. Okay, so here we are. This is where our code should be written. So we are going for reverse in order. So first we need to call our right child. So rwsol node dot right. Now we need to do some work. Let's say some work, and then we are going to call our left child rwsol node dot. Now what we are going to do in between these calls? So we need to replace node dot data with sum, and sum should be increased by node dot data. But if you look closely, we are changing our node dot data's value here, but we need the node dot data's original value. So we are going to store it in a temporary variable, the node dot data's original value, node dot data, and now we are going to add original value of the node dot data to our sum. Okay, now there is only one thing missing, the base case for if node dot equals null, then we need to return. Now let's see if it works. Okay, it's working for a sample test case. Now let's see if it works for all our test cases. So we got 10 out of 10, which means all our test cases are running perfectly on this logic. All right. So that's all for this video. See you in the next one.